Hey, Alejandro. Everything okay?
Yeah.
Ripper. Good. Okay, so this one has the registration list, so you can show this is the people who've registered.
Yeah.
Okay, so these are the 20 who have officially registered.
So if
And this.
someone is not here,
Look, yeah, we should keep them to that numbers. If there's someone not there, then maybe these ones can come in. But it's up to him to how he wants to deal with them.
yes, because someone asked me before if they can enjoy,
Well,
but it's not in the list.
it's not in the list. Well, it's we were told 20.
Okay.
We were told 20. So
Okay.
if the speaker wants to change it and he's happy with that, well, I guess it's okay for us. And you've got the recording thing done?
Yes, already.
You already started?
Yeah, yeah.
Super. Okay.
He's good.
Oh no, you should. What you should do is the session will, the one which will be recorded will be this one. So you can have it on both,
Oh, okay.
as long as it's on both. But this one is the one that's recorded.
Okay. Okay.
Yeah?
But he's good because the name teach them
Sorry. Do it.
who is good or
No, it's a man. It's a man. Yeah. Yeah. Sorry.
is here.
I haven't seen him
No,
today.
not here, but maybe.
He was here yesterday. I haven't. He's around. Yeah. 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 I didn't see him this morning, but he should be.
Okay.
Yeah.
Right on second.
All right. Where do we put? Oh, here it is. You want to record it or something? Welcome, everyone. Should we use the mic, or is this good enough for you? It's fine? Okay. I'm not a high-tech guy, so let me do it like this. My name is Thijs ten Ra. I always get my name, so I have to turn around. But I am affiliated with Tilburg University in the Netherlands, and I teach a number of courses there. Economics, chiefly microeconomics, and also math courses. This is sort of at the interface of the two. So the title of this course is Linear Programming in Input-Output Analysis, and it consists of 3 lectures. Today is the first lecture, and that is the theory of linear programming. Most of you may know linear programming, but I've decided to make the course self-contained. So if you already know, you may take a break and go to the loo or whatever, and return in due course. And then the second day, which is tomorrow, I'm going to present the theory of productivity and efficiency. And then finally, the third day, the day after tomorrow, it will be on applied equilibrium analysis. So computable equilibrium models. It's the culmination of this course. Okay, so today, the first lecture, linear programming. Now, many of you may be surprised that there is a course on input-output analysis and linear programming. Because, in linear programming, you maximize something, so you optimize, and you investigate so-called shadow prices, which we will analyze in detail. They're essentially competitive prices. So linear programming is very close to neoclassical economics, where you optimize things. Now, as we all know, input-output analysis is much broader than that, and is also of interest for the study of economies where things are not optimal. Even in those economies, there are interesting relationships to be studied. Like you have the material balances, so you can do multiplier analysis and things like that. So is there a connection? And the answer is yes, there is a connection. First of all, if the economy happens to be efficient, then there is perfect consistency between neoclassical economics, including linear programming on one hand and input-output analysis on the other hand, something we will demonstrate. And secondly, if the economy is not perfectly competitive, then it is very interesting to investigate how close the economy is to its production possibility frontier, because that will yield a measure of the inefficiency in the economy. And listen, guys, if you want to know where the frontier of an economy is, you have to do linear programming, because then you essentially determine how much output can be produced given the resources that are available to the economy. Okay? So that is the connection. Let me also motivate this course in terms of my own research program. In neoclassical economics, it's quite common to assume that there is perfect competition. Okay? Most input-output economists, including myself, don't like that assumption. Okay? Because in reality, it's violated for most economies. So if you don't make that assumption of perfect competition, things get a bit more difficult, like determining the performance of an economy, like total factor productivity growth. You know, if the economy is distorted, then the prices of, say, labor and capital are not the correct prices to use as value shares in your formula for total factor productivity growth. So you have to use something else. Okay? You have to use the hypothetical competitive prices. And again, to determine them, you need linear programming. Now, we're going to relate linear programming to input-output analysis, and as I mentioned, the course is self-contained, so I assume that you don't know input-output analysis, and therefore I'm going to review that quickly as well. So we divide the economy in a number of industries or sectors, N in total, so agriculture, mining, all types of manufacturing, etc. In traditional input-output analysis, each industry produces 1 unit of its output and consumes produced inputs, and the amount of produced input per unit of output is denoted by A sub ij, so that is the amount of I you need to produce 1 unit of j. That's an input coefficient. That's an intermediate input coefficient because it pertains to the produced inputs. There are also factor inputs, capital and labor. So to produce 1 unit of output in sector J, you need K sub J, and that's not very clear here, and L sub J of capital and labor. By the way, I have submitted my transparency to the organizer of this course, Jose Rueda Contuche, so I presume I had to submit it for dissemination among students. I don't think it's posted on Blackboard, but it's available, so it's not really necessary to take notes. Try to understand what I'm saying, and if you want a copy of my PowerPoint presentation, ask Jose, and he will kindly deliver it to you. So let us organize these coefficients. The input coefficients, if you look at input I, there is a row of the A matrix. So each input has a row, and the elements of a row tell you how much of that input is needed in a different industry. And we're going to add 2 more rows, one for the factor input capital and the other one for the labor input. So we have n plus 2 rows. Okay? And perhaps it's more interesting to look at the columns, because if you look at the columns, you get the input requirements to produce 1 unit of output. That's what Vasily Leontiev liked to call a recipe. So to produce 1 unit of product 1, you need A11 of input 1, A21 of input 2, all the way to AN1 of input N, and also L1 units of labor and K1 units of capital. And what Leontief called a recipe is called a technique. And for every product we have a technique, and if you stack them together you get that big A matrix plus that row vector of capital coefficients and the row vector of labor coefficients. And such a collection of techniques is called a technology. And in general, different techniques may coexist because you have firms producing product 1 and the firms may have different input coefficients. Mm-hmm. And then, of course, one of the interesting issues is to determine which of the two firms is the most efficient one. All right, let's carry on. The variable will be an output vector, x, so it's an n-dimensional column vector. And to produce the first component of x, x1, you need all those intermediate inputs. And we assume constants returns to scale, so we assume that you need A11 times x1 of input 1 plus A21 times x1 of input 2. And finally, L1 x1 labor and K1 x1 capital. Okay, so if you organize all that in a matrix, you get that the intermediate requirements are given by AX. And similarly, the labor requirements are LX. It's a scalar because L is a row vector and X is a column vector. And capital requirement would be KX. And then the first equation is this blue equation that is called the material balance. Okay, the final demand in the economy is what you produce minus what you need as intermediate inputs. And the final demand accrues to the households, to the businesses for investment, to the government for public consumption, and to net exports. And it's important to realize that if you're interested in the performance of an economy, think of the GDP in the economy, then you're talking about the final demand in the economy, not the gross output. I mean, if you would measure the output of an economy in terms of the X vector, you make a grave mistake. It's actually the mistake that was made in the Soviet Union early on, and Leontief identified that mistake, and that was the beginning of input-output analysis. Let me give you a very simple example of intermediate production. Car dealers, they have an intermediate input, namely a car. And what does a car dealer do? They attach a license plate to the car, and then they pass it on to the consumers. Okay? Now, if we would use the gross output as a measure for GDP, then we would first have the car produced by the factory without a license plate, and then we would have the car produced by the dealer with a license plate. So the output would be 2 cars and 1 license plate. And that would be an overestimate of the output of the economy because it produces only 1 car and 1 license plate. Okay, so that is why we use the net output to measure GDP. Now, this equation is used for multiplier analysis. So this is the same equation, and if I solve that equation for the gross outputs, I get the following solution. X equals I plus a squared, etc., all the higher powers times y. If you want to check that that is the solution, it's fairly easy. So on the, I simply substituted on the right-hand side. This is just a verification. So the first term on the right-hand side is x, and I substitute I plus a squared, etc., times y. And then the remainder on the right-hand side is minus a times x, and therefore x, I substitute again I plus a squared, etc., times y. Okay, and then what we get is that the in this black expression there are two parts, and in the left-hand side, the second term is ay, and it cancels against the first term in the second part, because that is a times I times y. And similarly, the third term in the first part cancels out against the second term in the second part. So all that remains is the first term in the first part, and that is simply y. This is a very neat solution, because it tells you that if you want to satisfy final demand y, exercised by the household, the government, and abroad, then what you have to produce is y itself, but you also have to produce the inputs required to produce y, which is ay, and you have to produce the inputs required to produce the inputs of y, that is a times ay. Okay? This is called the Neumann series. And you get a multiplier effect, because to supply a net output of y, you have to produce more than y. You also have to produce the inputs. If you pre-multiply this solution by the labor coefficients, you get the employment multipliers. So that tells you how much labor is required to produce your net output vector y. Okay, if you then substitute for net output vector y, say the first unit vector, which has a 1 in the first entry and 0 in all the other entries, you get the amount of labor that is necessary to supply 1 unit of final demand of product 1 to the households, the government, investment, or the foreign countries. Okay? So that is the amount of labor that is embodied in 1 unit of the product. That is precisely the same as the Marxian value of a product. Okay? And you can also do the same thing for capital. You can, if you want to, you can endogenize capital and consider that as a produced commodity, but that gets too complicated for this course, so I'm not going to do that in this framework. Now, let us look at the value system, because thus far we have investigated the relationship between the net outputs in the economy, household demand, and all the other components of final demand on one hand, and what has to be produced on the other hand. Okay? That is the material balance equation. Now, Leontiev worked with a second equation, which is the value equation. Okay? He called that a dual equation, because basically you have to transpose everything. And indeed, as we shall see later, there is a clear connection with duality analysis that is used in linear programming, something I'll define a little later. Okay? So let us look at production sector J. So if J is 1, it would be agriculture. The inputs per unit of output are Aij for the intermediate inputs I, Kj for capital, and Lj for labor. Now, certainly if we include profit in the cost of capital, we get the following value relation. The price of 1 unit of output in industry J is equal to the material costs, Pi Aij, and I sum them over I. So that is, the cost of electricity and all the other produced inputs, plus the cost of capital, plus the cost of labor. And this happens to be the jth component of a vector equation. So on the left-hand side, I have a row vector P, a row vector. Mind you, I always use row vectors for prices and column vectors for outputs. And then the first component is going to be PA. So that is the intermediate costs plus the capital cost and the labor costs, all per unit. And then you can do the same thing, at least given a rental rate and a wage rate. And indeed, Leontiev considered that to be given. He didn't really explain the relative factor input prices. We will do that later. I mean, there you have to use neoclassical economics. Then you can solve for the prices. Okay, you just take that equation, P equals PA plus RK plus WL, and in exactly the same way as before, the solution is that the price vector equals the RK plus WL, and mind you, K was a row vector of capital coefficients, L was a row vector of labor coefficients, R is a scalar, the rental rate of capital, W is a scalar, the wage rate of labor, so that RK plus WL is the unit factor costs. It's the factor costs per unit of output. And if you multiply it through by I plus A squared, that same Neumann series, it's also called the Leontiev inverse, you get the prices. Okay? So what you get is that the price of a commodity is the factor costs plus the factor costs of the required inputs plus the factor costs of the inputs etc. So you express all the prices in terms of factor costs. So this analysis mirrors the previous analysis. Now, there is a very simple connection between the two, and that is the following. I'm beginning with the final demand in economy, Y. That's a column vector. So Y1 is the net output of commodity 1, etc. And I pre-multiply by a row vector of prices, so I get the value of the net output in economy. Okay? Now, that is the gross domestic product. Remember, when we calculate the gross domestic product in the economy, we take the net output in the economy and we value everything. Now, in the first equation, I'm using the material balance, so the net output equals the gross output minus the intermediate inputs. Okay? And then I factor out the gross output vector, so I get P minus PA times X, and then I use the last just derived equation, which stated that the prices are equal to the material costs plus the factor costs. So P is equal to PA plus RK plus WL, and therefore P minus PA is RK plus WL. That's a clear substitution. And then, what do I get? I get an inner product of unit vector costs, RK plus WL, with gross outputs. Okay, so if I take the first component, it is the capital and labor costs in Industry 1. And then the same thing in Industry 2. So I get what is earned in all the industries, and that is national income. So we have seen that the national product equals national income. This is a macro identity which is not true at the industry level. I mean, this is true only for the sums. A very nice example is the business services. In the business services, a lot of money is earned, so you have a fine contribution to the expression on the right-hand side of this string of equations. Okay, there is a lot of capital and labor employed in the business services. You multiply it by the rental rate and the wage rate, and you multiply it by the gross output of the business services, and you get income. The contribution to the left-hand side is 0, ladies and gentlemen, because services are divided in personal services, which are the services used by the households and other components of final demand, and business services are services used by the industries. So they are intermediate inputs. But we have subtracted out those intermediate inputs because on the left-hand side we have only the net output. Okay? So the equality between product and income is a macro identity. That was quick. That was input-output analysis. So now the real thing, linear programming. And it'll be very easy to generalize it to more variables, but so let me begin with two variables, say x1 and x2, and two constraints. In the general format, a constraint is an inequality. Sometimes you may have equalities as constraints, but that is just a pair of inequality constraints. Right? If you have the constraint, for example, x is equal to y, it is the combination of x is less than or equal to y and x is greater than or equal to y. Okay? So this is fairly general. In a constraint, you have the variables on the left-hand side with coefficients, and coefficients are denoted by C of coefficient. So if you look at the subscripts, then the first subscript indexes the constraint, and the second subscript indexes the variable. And on the right-hand side, we have the bounds, B for bound. So here there are two constraints. And an example is the production of two goods with a capital constraint and a labor constraint that fits in this framework. Now, in linear programming, you maximize something, a linear function of the variables, subject to linear constraints. That's the definition of linear programming. Okay. The objective function, you have only one objective function because otherwise there would be a conflict and you would be in the field of game theory instead of linear programming, although there is a connection, but here I'll stick to linear programming. So we have our variables x1 and x2, and they have objective function coefficients a1 and a2. Okay? For example, if the objective function coefficients are the prices of the goods, say in world markets, when an economy is a price taker, then the objective of the economy might be to maximize revenue. It is important to have a very concise understanding of a linear program. A linear program is a triplet A, B, C. Okay? A are the coefficients of the objective function. B are the bounds in the constraints, and C are the coefficients in the constraints. So if you have a triplet A, B, C, you have a linear program, right? Now, this is really linear programming in one lesson I'm going to do today. I think I have an hour and a half, if I'm not mistaken. So I should be finished by 4 o'clock, right? Is that correct? All right. 3:30, yeah, sorry. I'm not very good at calculus. Let me see how you're doing. Yeah, that's all right. Yeah. Okay. So this is the same example. So we have two variables. And we have two constraints. In linear programming, both the objective function and the constraints are linear. That's why it's called linear programming. If they're not linear, it's called nonlinear programming. And the combination of linear and nonlinear programming is called mathematical programming, to distinguish it from programming in the sense of computer codes and so on. So we have two constraints, constraint 1 and constraint 2. There are inequalities. So what I've depicted here is the boundary of a constraint. So the feasible set, all the points with components x1 and x2 that fulfill both constraints, is on one side of such a straight line. And since that's true for both constraints, and let us assume that things have to be smaller than or equal to a bound, and that the coefficients are positive, it's not really necessary, but just in this example, then it means that the feasible set is under the straight line of constraint 1, and it's also under the straight line of constraint 2. So everything under that kink line is feasible, okay? And then we have three indifference curves. In linear programming, the indifference curves are all straight lines by linearity. So in this case, the farther you go to the northeast, the better off you are, okay? And so we see that x star will be the solution, okay? Now, if those indifference curves would be much flatter, okay, then x star would no longer be optimal. If they would be nearly horizontal, then what you would do is you would be on the boundary of your feasible set, and you would wander in northwestern direction. But in that case, there is no solution. The solution would be infinite, okay? So I'm going to focus on linear programs that have a solution. And it's really a mathematical detail to identify the linear programs A, B, C within the class of all linear programs that have a solution. Okay? It's a minor technical question, and I just iron it out. So when we have a solution, we have this situation, x star. And if you understand this picture, then you will also understand the quintessence of linear programming. So let me look at one of the indifference curves. So any indifference curve is given by the formula that a1 x1 plus a2 x2 is constant. So the greater the constant, the farther you are to the northeast. So if you solve that equation for x2, then you get x2 is constant over a2, so that's some other constant, minus a1 over a2 times x1. So that is the slope of the indifference curve. Okay? Again, minus a1 over a2 is the slope of the indifference curve. Now, let me give you the example again where the indifference curve is horizontal. The indifference curve is horizontal if and only if a1 is equal to 0. Okay? So then the objective function would be x2 essentially, okay, times a2, but if a2 is positive, say 2, then instead of an objective function of 2x2, you can just as well use x2. If you want to find the hottest place on Earth, it doesn't really matter if you measure temperature in Celsius or Fahrenheit. Okay, so whenever you have an objective function, you can always apply a monotonic transformation. So a horizontal indifference curve is essentially given by the case where a1 is equal to 0 and a2 is equal to 1. There is no pointer, but that is this vector. This is the vector where a1 is equal to 0 and a2 is equal to 1, right? And notice that this vector is perpendicular to that horizontal line, okay? So similarly, in the original plot, where these are the indifference curve, this is a1, a2. So that is the vector of objective function coefficients, okay? In this case, a2 is bigger than a1, because if you look at the formula of this straight line, I mean, it's a relatively flat line, so a1 over a2 is less than 1, and therefore a2 is bigger than a1, okay? So a flat line means that the direction of the objective function a1, a2 is pointing upwards, okay? Similarly, if you would have a vertical indifference curve, like here, then a1 is equal to 1 and a2 is equal to 0, okay? So those little arrows tell you in which direction the value of an objective function, or a constraint function for that matter, or a non-negativity constraint. I do not assume that variables are non-negative. I could, I mean, x1 greater than or equal to 0 is fine. It's just another constraint, and it's important to treat it as just another constraint. Okay, many people think that in linear programming, when you look at the so-called dual relations, which we will do in a moment, you have to flip everything. Like you take the transpose of the matrix and you flip the inequalities and so on. That is not true, as we shall see in a moment. It happens to be true for a specific subclass of linear programs, namely linear programs with non-negative variables, and I shall point it out in detail. But it's a very mechanical and misleading point of view, okay? So I prefer this geometric point of view. Now, shadow prices. We will use the tangency of the kink feasible boundary and the isoquant to characterize the optimum, okay? If you look at the thin indifference curve, and it is just tangent to the thick boundary of the constraint set. If you would have a smooth nonlinear function, it would be precise tangency in the sense that the slopes are equal. But here, in a sense, you still have tangency between that thick line and that thin line, right? They just touch each other in a single point. That condition is enough to characterize the solution of a linear program and to derive the main result of linear programming, which is called the main theorem of linear programming, that associates the value of a dual program, something that remains to be specified, with the value of the linear program you start with, which is called the primal program. Okay, so the tangency condition is crucial. So there is a common slope there, and that common slope is determined by the shadow prices. We will be crystal clear about those shadow prices in the transparencies to come. And those shadow prices will prove very handy because they are productivity measures. They tell you by how much the value of the objective function goes up if you relax a constraint by 1 unit. So if these two constraints were the labor constraint and the capital constraint, you add a worker to the economy, then the shadow price will tell you how much more output you get. Okay? The shadow prices will also be very useful implicit prices for environmental hazards. We will look at that. Oftentimes environmental hazards are not priced in a free market, but better should be priced, according to the polluter pays principle, something we will explain in detail. So shadow prices will be idealized competitive prices in the situation where you have perfect and complete markets. So now let us look at that first order condition. We have that tangency condition. Now, in linear programming, you don't have perfect equality of the slope of the constraint function and the slope of the objective function, for the simple reason that in that kink, the slope of the constraint function is not a well-defined thing. If you start with a relatively flat slope, say a slope of -1/2, and then it changes into a slope of -1, okay, then the tangency condition tells you that the slope of the objective function is somewhere between -1/2 and -1. That's all you know in linear programming, okay, because of that kink condition. So here it is. What we do have to figure out is which one was the steepest, and I forgot. Okay. So constraint 1 is relatively flat, and constraint 1 has slope minus C11 over C12. Constraint 2 is relatively steep, and constraint 2 has slope minus C21 over C22. Remember, the first index of a constraint coefficient tells you which constraint you're talking about, and the second index tells you which variable you're talking about. The slope of the objective function is minus A1 over A2, okay? So all we know is that the slope of the objective function, A1 over A2, is in between the two slopes of the two constraint functions. Okay? And constraint 2 is the steep constraint. So we put, multiplying through those negative slopes by -1, we get the absolute values, and we get that the slope of the objective function A1 over A2 is in between the slopes of the relatively flat portion of the constraint C11 over C12 and a relatively steep portion of the constraint C21 over C22. Okay? Now this inequality is really crucial. If you're lost, raise your hand and I'll put you back on track. Because if you're lost here, then, you may consider to take one of the other two courses. And so again, this condition just characterizes optimality, the tangency between an indifference curve of the objective function on one hand and the slope of the constraint function on the other hand. And since we happen to be in a kink of that constraint function, there is not a single equality, but we have a pair of inequalities. Yeah? So there it is. This is the geometry of the situation. Okay? This is again the thick kink line is the boundary of the feasible set. So under that kink line you have all the points that fulfill both constraints. The thin line is the indifference curve. Okay? Now remember that if you look at the vector a1, a2, so the coefficients of a straight line, you get the vector that is perpendicular to that indifference curve. For example, when we had a horizontal line, that line was just sticking upward, it was the vector 0, 1. Okay? And in general, it's the vector a1, a2. So, and we can do the same thing for the two portions of the boundary of the feasible set. So the upper part of the feasible set is a relatively flat line. That was the first constraint. Okay? So the little arrow that is pointing upward, what are the components of that little arrow? Can anyone tell me? Yeah, and of which constraint? Pardon? Yeah, which constraint was it again? No, the arrow pointing upward corresponds to the flat constraint. Okay, and what was the flat constraint again? The first. So what are the components of that little arrow? Right. And similarly, the little arrow which is pointing a bit more to the east is the vector C21, C22. Okay? Now, the objective function coefficients A1, A2 are in between. That's the tangency condition, remember? So A1, A2 is in between C11, C12 on one hand and C21, C22 on the other hand. And since it is in between, it must be that the vector of objective function coefficients is a non-negative combination of the vectors of the constraints. Okay, so it is lambda 1, the scalar, non-negative, times the first constraint coefficients vector plus lambda 2 times the second constraint vector. Okay? Because if you look at all non-negative combinations of those two constraint vectors, you get the ice cream cone that is spanned by those two little vectors. And we know that the vector of objective function coefficients is somewhere in the ice cream cone. Okay? So it is some non-negative combination of the constraint coefficient vectors. All right? Yeah?
Is this something that you cannot do for polar solution?
No, then the logic is the same. What I'm going to derive are the so-called first order conditions, and they are exactly the same as the first order conditions in microeconomics, where you maximize your utility subject to a budget constraint. What you use is the tangency between an indifference curve and the budget line. That's what I'm using. If you want to look at corner solutions, all you do is you add another constraint, like x1 is greater than or equal to 0, or x2 is greater than or equal to 0, or both. Okay? And then if you absorb those non-negativity constraints, you get that the standard first order conditions, which is the so-called Lagrangian condition, something I'll explain in a moment, will reduce to the Kuhn-Tucker conditions. But it's just a special case. Okay? It is just a case where some of the constraints reflect non-negativity. So strictly speaking, there is no reason to pay special attention to it. All right. So again, optimality is characterized by the condition that an indifference curve is tangent to the boundary of the feasible set. And that tangency condition is translated in the condition that the vector of objective function coefficients is a non-negative combination of the vectors of the constraint coefficients. The weights in that non-negative combination are lambda 1 and lambda 2. Lambda 1 and lambda 2 are the Lagrange multipliers. This is basically it. So lambda is Greek for L, and L is the first letter of Lagrange, a French mathematician. And this is it, folks. I mean, all the theory is based on this. So we will demonstrate that these are shadow prices. We will demonstrate that these measure marginal productivities. We will derive the main theorem of linear programming. But the thing to bear in mind is this geometry. Okay, so here it is again, the first order condition. The first order condition states that the vector of objective function coefficients is a non-negative combination of the vectors of the constraint coefficients. Okay? A1, A2 is also called the derivative of the objective function, because the objective function is A1 x1 plus A2 x2. It's a function of two variables. So you can differentiate it with respect to x1, and you can differentiate it with respect to x2. If you stack those so-called partial derivatives in a row vector, you get A1, A2. That row vector of partial derivatives is called the derivative. Okay, if you have a function of several variables, then the derivative is a row vector. Okay, so what we have as optimality condition is that the derivative of the objective function is a combination, a non-negative combination of the derivatives of the constraint function. Okay? This is why people set up the so-called Lagrangian function. I mean, I don't do it because it's very mechanical, but a Lagrangian function is the following. You take your objective function, and then minus lambda times the constraint function. Okay? That's called the Lagrangian function. And then you treat it as a function to be optimized. Now, if you call the objective function f and the constraint function g, the Lagrangian function is f minus lambda g. And if you treat it like a free optimization problem, you get So you just take the derivative, you get f prime minus lambda g prime is equal to 0. And therefore f prime is equal to lambda times g prime. The derivative of the objective function equals lambda times the derivative of the constraint function. It's exactly the same. But you understand the setting up of a Lagrangian function only after you have seen this. This is the reason why you set up that Lagrangian function. Again, that is a mechanical trick to implement this, okay? But I prefer, I always bear in mind that geometry of those three arrows in the previous slide. All right, the weights in this expression, lambda 1 and lambda 2, constitute accounting prices, one for each constraint. Lambda 1 will value capital because, the first constraint was a capital constraint, and it's called the shadow rental rate. And lambda 2 will value labor if the second constraint is the labor constraint. Okay, same equation again, third time, exactly the same equation. So on the left-hand side, the first component of the equation, so in other words, A1, interrelates the coefficient, that should be singular, not plural, of the first variable, x1, with the objective coefficients the first component, it's a bit very confused. It interrelates the objective function coefficient A1 with the constraint coefficients on the right-hand side, C11 and C21. Okay? So if you take the first component of this equation, you get A1 equals lambda 1 C11 plus lambda 2 C21. Okay? So that pertains to the first variable x1. So we have lambda 1 C11 plus lambda 2 C21. So the lambdas correspond to the first index of a constraint coefficient. The first index of a constraint coefficient indexes the constraint. So a lambda is, with every constraint we have one lambda. That's the idea. Okay? So for every constraint we have a lambda. Now lambda 1 and lambda 2 are a way, if you determine lambda 1 and lambda 2, that's a way to solve a linear program through the dual. And it may be very efficient, particularly when you have fewer constraints than you have variables, because the dimension of a linear program is the number of variables. Okay? If you have very many variables but only a few constraints, and you can figure out lambda 1 and lambda 2, then, as we shall see in a minute, you have solved the problem. Okay, now in the bottom of this, transparencies are generalized to more constraints. So you have lambda 1 times the first constraint plus lambda 2 times the second constraint plus lambda 3 times the third constraint, etc. Wow, same equation again, or is it? Or yeah. Okay, so let us look at the same equation, but now in the context of a capital and a labor constraint. So the first component of the equation, A1, if we maximize the value of the net output in the economy subject to a labor and capital constraint, then A1 is going to be the world price of product 1. Remember, we look at a small open economy, it just wants to maximize the value of its net output, making as much money as you can, because then you can buy whatever you want to buy in world markets. So then A1 is going to be the price of the world price of good 1. And on the right-hand side, we have lambda 1, C11 plus lambda 2, C21. Now C11 was from the capital constraint, and that was the amount of capital needed to produce 1 unit of commodity 1, and C21 is the labor constraint. So C21 would be the amount of labor needed to produce 1 unit of commodity 1. So what you get is that the price of product 1 is going to be the value of capital plus the value of labor, all on a per unit of output basis. But here, that is a big distinction with Leontief. The input prices, the vector input prices of capital and labor are endogenous, because the lambda 1 and lambda 2 are determined by that geometry of the solution. Okay? So what you get is the same connection between prices and vector costs as we have seen in input-output analysis, with, however, endogenous prices of the vector inputs. All right. So the shadow prices, lambda 1 and lambda 2, are competitive prices in the sense that price is exactly equal to cost. There are no profits. And that is the next step. We will show that not only profits are 0, but those shadow prices will measure the marginal productivity of the 2 vector inputs. Now, marginal productivity is something Leontief would never use, because in standard input-output analysis there is no, there is nothing marginal. But in linear programming there is, and later on we will connect it with standard input-output analysis by distinguishing the position of an economy vis-a-vis its frontier. And if you want to find the inefficiency of an economy, you basically want to find how close it is to its frontier, and then a natural metric to measure that distance will be given by those shadow prices. Now, this is just for the record. Okay, I'm doing precisely the same thing as before, but not 2 variables, but n variables. Okay, not 2 constraints, but m constraints. Okay, so we maximize the objective function. There are n variables, and the objective function coefficients are a1 through an, subject to the first constraint, c11 x1 plus c1n xn less than or equal to b1. And then you repeat it for the other constraints, and n is the last constraint. Okay? So this, again, is the general format of a linear program ABC, where A is the row vector of objective function coefficients, B is the column vector of bounds, and C is the matrix of constraint coefficients. And a constraint is represented by a row out of your coefficient matrix. Okay, and then here's the generalization of the geometry of the solution. The solution is characterized by the condition that the little arrow associated with your indifference curve And that was simply the row vector of objective function coefficients, a1 through an, is a non-negative combination of the little arrows of the constraint function. Okay? Because it has to be in that ice cream cone. If it weren't in that ice cream cone, you could wander all the way to the northwest or to the southeast. Things would go off to infinity. There would be no solution. And once again, I confine our attention to linear programs with a solution. So then you have this situation. The bounds do not feature in this equation. That is interesting, right? I mean, a linear program is defined by A, B, C. B were the bounds. But if you look at this so-called dual equation, you find A and C, but you don't find B. Now, a bound may be non-binding. For example, if you have two constraints which are parallel, okay, so they have the same slope, but one is under the other, then the first constraint will be binding and the second constraint will be non-binding, right? If you have x1 plus x2 is less than or equal to 5, and you also have x1 plus x2 is less than or equal to 6, then the first constraint is going to be binding, and the second constraint is going to be non-binding. Okay? Now, a non-binding constraint will not pop up in the dual equation. And the only way that you do not pop up in the dual equation is what? Suppose the first constraint is non-binding, okay? Now, if the first constraint does not show up in the dual equation, we may conclude what? Pardon? Well, yeah, what is 0? Right. If a constraint is non-binding, then its Lagrange multiplier will be 0. Right. Roughly speaking, but this is very rough, this holds only if you have independence, something I'm not going to discuss. The number of binding constraints equals the number of variables. Because if you have very many constraints, there's a deep mathematical fact that if you look in n-dimensional space and a constraint is characterized by that little arrow which is perpendicular to that constraint, if you have more than n constraints, so if m is greater than n, you have more of those little vectors than there are variables. And there is a deep mathematical fact that tells if you have more vectors than the dimension, those vectors must be linearly dependent. And it's because of that linear dependence that some of the constraints will be implied by other constraints, and therefore non-binding. Okay, so that explains that intuition. All right. If you like matrix notation, here it is again. First we have a linear program. We maximize AX, where X is the variable, subject to Cx is less than or equal to B. And then the dual condition is lambda C is equal to A and lambda non-negative. Okay, and the dual condition is equality. Okay, it is because we have the tangency condition, and the tangency condition, as in microeconomics, where the slope of an indifference curve is the slope of the budget line, in other words, where the first order condition of the consumer is that the marginal rate of substitution is equal to the price ratio is an equality. And likewise, we have an equality here as well. So we didn't flip the inequality of the primal program into an inequality in the dual program. In general, that's not true. That's true only in a special case. You can determine the lambda by minimizing the value of the bounds. So if you have a capital and a labor bound, that would be minimizing the vector, minimizing the endowment of capital and labor in the economy. That is something I'll explain later. So constraints are rows in the C matrix, and the primal program shows them. In the dual program, you do not have C times X. C times X is a combination of the columns of the C matrix, but in the dual program you have lambda C, so that is a combination of the rows of C matrix. So again, you have a non-negative combination of constraints, and constraints are rows of the C matrix. All right. Again, we started with a linear program, max AX subject to CX is less than or equal to B. This is what I've explained before. This is how you set up the Lagrangian function. You take AX minus lambda times the constraint function CX. You can also throw in the B, the coefficient of bounds. I don't always do it, but most people do it. So you take lambda times B minus CX. B minus CX is called slack because the constraint was CX is less than or equal to B. So if there is any slack in that constraint, it will be B minus CX. Okay, so the Lagrangian function is the ordinary objective function AX plus lambda times the slack. Okay, this is a mechanical way of analyzing the problem, but many people are familiar with it, so let me review it. If you set up this Lagrangian function and you take the derivative with respect to x, you first get a. It's a linear function, so differentiating with respect to x yields a. And if you differentiate the second term, you get minus lambda c as the derivative. Relegating that to the right-hand side, I get a is equal to lambda c. That is precisely the first order condition of linear programming. Remember, a was a non-negative combination of the constraints, and the constraints were the rows of the C matrix. If you take the derivative of the Lagrangian function with respect to lambda, what do you get? Now I'm using your observation, because this happens to be a case where you minimize something with respect to a non-negative variable. Because those Lagrange multipliers were non-negative. Okay, so you have two possibilities. Either you get an ordinary solution where the derivative is equal to 0, so then the derivative with respect to lambda, it's b minus cx. If that is 0, you get cx is equal to b. Or you get a corner solution where lambda is equal to 0. Okay? So this is a fundamental insight. It basically tells you that either a constraint is binding or the constraint is non-binding, and then lambda is equal to 0, as we've seen before. Right? Now this may look very trivial to you, but it's a very powerful observation, and we get a lot of mileage out of this. Okay? This also explains why the dual constraint is an equality. So now we're going to derive a first result of the theory of linear programming, and that is complementary slackness. We know what slack is. There is the slack in the primal constraint is simply b minus cx. You have that inequality. If there's any room, it's equal to b minus cx. Okay, you may also have slack in the condition that lambda is greater than or equal to 0. It's an inequality, so there may be slack. Okay, if lambda is equal to 3, then the slack is also equal to 3, because 3 is greater or equal to 0, but the slack is 3. All right. Now this is a lot of stuff. Personally, I don't find it too important, but every time I teach linear programming, I have to address the misconception with many students that in linear programming you take the transpose of constraint coefficients, you flip the inequalities, and that whole array of mechanical tricks, and that's how you get the dual. Okay? It's not true, because in linear programming you have an inequality in the primal program, namely Cx is less than or equal to b, and you have an equality in the dual, namely A is equal to lambda c, because your objective function is a non-negative combination of the constraint functions. Okay? Now, where does that misconception come from? Well, it is actually true for a special class of linear programs, namely linear programs with non-negative variables. Okay? So here it is. This is a linear program with the same objective function, AX. I also have constraints Cx less than or equal to b plus non-negativity constraints. Okay? But that is just like adding some rows to your C matrix. For example, the first non-negativity constraint is where you have a -1 in the first cell and all others 0. And a 0 bound, because then you get -1 times x1 is greater than or equal to 0. No, we had as bounds, we had Cx less than or equal to b, so we get -1 x1 less than or equal to 0, and that is the same as plus x1 greater than or equal to 0. Okay, so a simple constraint with a -1 in the first component and zeros for the rest is equivalent to non-negativity of the first variable. Okay, so now I'm going to apply the same logic that the derivative of the objective function a1 an is a non-negative combination of all the constraints. So we have lambda 1 times the first constraint, plus lambda m times the mth constraint, plus sigma 1 times the first non-negativity constraint. Okay? So sigma 1 is yet another yet another Lagrange multiplier. And the first non-negativity constraint, remember, is represented by -1, 0, 0, 0, etc. Plus sigma n times the last non-negativity constraint, which is zeros everywhere, and a -1 in the last entry. All the Lagrange multipliers, lambda 1 through lambda m, are non-negative, and sigma 1 through sigma n are non-negative too. This is classical notation. Sigma is Greek for S, and S is the S of slack. So this equality is now the first order condition. Okay? Now on the left hand side we have A. On the right hand side we have lambda C minus sigma. But sigma is greater than or equal to 0. Okay? So if A is equal to lambda C minus sigma, that is equivalent, eliminating sigma, to A is less than or equal to lambda C. Okay? Because sigma is non-negative, like any Lagrange multiplier. So now your first order condition is that A is less than or equal to lambda sigma. That A is less than or equal to lambda C. And this is what people do when they set up the dual. They transpose things, so instead of post-multiplying with a column vector of variables x, they pre-multiply with a row vector of Lagrange multipliers lambda. That's equivalent to taking the transpose of the C matrix. And they replace the inequality in the primal constraint by a flipped inequality in the dual constraint. So that's an okay procedure for linear programs with non-negative variables. All right. Now the phenomenon of complementary slackness. Okay? Remember, non-binding constraints play no role. They may be ignored. And the only way to ignore them is that their weight in the first order condition is equal to 0. Okay? So if a constraint happens to be non-binding, then the star represents the solution to the linear program. So if constraint I, so that is the ith row vector out of the C matrix, times x star is strictly less than bi, then the ith constraint is non-binding. Okay? So the Lagrange multiplier will be 0. So what we get is that the product of the Lagrange multiplier and the slack in the constraint is equal to 0. For all constraints. For the binding constraints, that is true because the slack will be 0, and for the non-binding constraint, that is true because the weight will be 0. Okay, so the product of the Lagrange multiplier and the slack in the constraint is equal to 0. Now this is called complementary slackness. Why? Because in the dual constraint was simply that lambda is greater than or equal to 0. All the Lagrange multipliers are non-negative. Okay? So the slack is equal to lambda. If lambda is 5, you have 5 is greater than or equal to 0. And indeed the slack in that inequality is 5. Okay? So lambda is not only a Lagrange multiplier, it's also the slack in the dual constraint lambda greater than or equal to 0. So you have that the product of the slack in the dual constraint, lambda I, and the slack in the primal constraint, the ith component of b minus cx, is equal to 0. Okay? So since the product of those two slacks is 0, it must be that if you have slack in one, you can have no slack in the other, because the product must be 0. Okay, slack in one, no slack in the other, complementary slackness. Okay, that's why this condition is called complementary slackness. Okay, so this simply reflects the fact that if a constraint is non-binding, then it will carry no weight in the first order condition. The lambda will be equal to 0. Okay, and conversely, if a lambda is positive, then the constraint must be binding. This is a very simple but powerful observation, and you have to understand this. So, demand further explanation if you're lost, because, All right, you won't believe it, but in an hour and a half we have accomplished what we want to accomplish. We prove now the deepest result of linear programming, and that's called the main theorem of linear programming. I begin with the phenomenon of complementary slackness of the ith constraint. So the product of the weight in the dual condition, lambda I, and the slack in the ith constraint is equal to 0. All right. This is true for every constraint I. Now on the left-hand side, I'm going to set up the value of the bounds of the primal constraint under the Lagrange multipliers, lambda 1 through lambda m. Okay, and then I substitute that first equation for every constraint. So for the first constraint, lambda 1 b1 is equal to lambda 1 c11 x star 1. And then we have to include c1n x star n. And you repeat it for the other constraints. I copy the left-hand side, and now on the right-hand side, what do we have? We have lambda. So first look at all the leading terms on the right-hand side. Each time it is something multiplied by x star 1. And the something is lambda 1 c11 plus dot 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 lambda m cm1. So that is that combination of constraint coefficients. But the first order condition was that that combination of constraint coefficients is precisely equal to the derivative of the objective function, a1. Remember, lambda c is equal to a. The objective function coefficients are a non-negative combination of the constraint coefficients. So lambda 1 c11 plus dot 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 lambda m cm1 is precisely equal to a1. That is the first order condition of constraint optimization. So on the right hand side we get the value of x star under the objective function coefficient. So that is the value of the linear program. On the left hand side we have the value of the bounds, but now valued, for every constraint we have one bound, now valued by those Lagrange multipliers. Okay? So we have that the value of the primal program, ax star, is equal to the value of the bounds. Now, if we were maximizing the value of the net output of a small open economy, then the right-hand side would have been the value of the net output of the economy under the world prices. Okay, so that is the national product. And then on the left-hand side, we would have the value of the constraining entities in the economy, capital and labor, but under endogenous prices, rental rate and a wage rate. And that would be national income again. So there's the same connection, but there is a little more structure than in Leontief's model, because now those factor input prices are endogenous. Good timing, it seems. There's one remark I want to make. This also explains you why those Lagrange multipliers are marginal productivities. Because look at the left-hand side. Suppose the first constraint is the labor constraint. So B1 is the labor force in the economy. Okay? Throw in another worker in this economy. So B1 goes up by 1, then the value goes up on the left-hand side by lambda 1. Right? So the value of your objective function of the primal program goes up by lambda 1. So lambda 1 is the marginal product of that worker. Okay? And this is why Lagrange multipliers are productivities. And this is why the theory of productivity analysis is based on Lagrange multipliers. Of course, we relate total factor productivity analysis to the solar residual, but it is perfectly consistent with this approach, and that is something that will be clear at the end of the lecture tomorrow. So let us now choose between questions and answers on one hand and tea on the other hand. She votes by her. I think that's a clear answer. Thank you for your attention. And tomorrow the show will go on.
Can I get this module?
Jose Rueda Cantucci, he's the chair of the scientific program. Rueda
Thank you so much.
Cantucci. Yeah, everything is good except the Rueda. He walks around somewhere. He's pretty well known. Just ask anyone for Jose. He's a big guy.
Can I have a quick question?
Yeah.
I didn't get what lambda you slash.
Oh, that's simply because the constraint in the dual program is simply
Yeah,
this.
he said the name is Jose
So the slack is lambda itself.
Cantucci.
So that is true only if the right hand side happens to be 0.
Yes.
Yeah.
Maybe. Let me talk you about this one. I will ask you tomorrow in the next session.
Oh, you missed the very beginning of my course because it's. I've submitted it to the organizer of this course, Jose Rueda Cantucci. He's the chair of the scientific program, and he has it. Yeah. Yeah, he should either email it to you or post it on Blackboard. I think that would be more practical. Or on the website, I mean. Yeah. He's a big Spanish guy. He's the chair of the scientific program. Ask anyone for Jose, and like most Spanish folks, he's called Jose. Yeah.
I also do some linear program about the carbon emissions recently.
About what?
Carbon emission.
Okay, yeah, I'll be talking about that. Yeah.